In this video, we're going to talk about dienes in conjugation and stability of molecules. So here we have one diene, and let's name it because we want to be practicing always our nomenclature. So say 1, 2, 3, and 4. So this is 1, 2, butadiene. So remember we do where the double bond starts. Diene. So diene, and this is 1, 2, 3, and 4. So this is 1, 3, butadiene, and this is 1, 2, 3, 4, and 5. So this is 1, 4, penta, so it's 5 carbons, pentadiene. All right, so but what we see here is that in this molecule, this carbon right here is sp2 hybridized. This one also is sp2 hybridized. But the one in the center is sp. So we can do this in another drawing. Say that I'm drawing here just the sigma bonds. The center carbon is sp hybridized. So we will have 1p unhybridized orbital that is actually making a pi bond with its neighbor. So I'm going to do just pi here in the sigma. And at the center carbon, we also have another unhybridized, I'm making another color, another unhybridized orbital that's actually perpendicular with the first. And that is making a double bond with the first carbon. Here, of course, you have bonds to hydrogen. Point is that the central carbon, one pi bond is in this plane and the other is perpendicular. So there is no electron delocalization. We call that type of diene cumulated. And important to recognize that there is no electron delocalization over these 3 carbons. And so when we have the other system on the right, here we have sp2 hybridized, sp2 hybridized. Same here, sp2, sp2. So now we can have a system in which we have all of the pi orbitals parallel to each other. So I can do this drawing. Again, the lines are the sigma bond, but I can have that. And now I will have possible overlap here, of course, and here. But I could also have that. What that means is electrons are delocalized all over. So that we call a conjugated system. So it's conjugated. It is a conjugated diene when we can do that electron delocalization. Notice that is when you see the picture here without the orbitals, we see double, single, double, so it is alternating. Here it's not, it's double, double. Now in the other compound, we will have sp2 hybridized, sp2 hybridized. Now this one is sp3. And I'm gonna draw the 2 hydrogens here. So in a different plane, right, respect to the other 2 bonds. Here you have sp2 at carbon 4, sp2 is also carbon 5. So now what happens is that this is no longer conjugated. This is prevented, the electron delocalization, by this sp3 carbon. We cannot move those electrons around. So because of that, we're gonna call that system isolated. So we have one pi system and another pi system over there. So they are isolated. And in terms of stabilization, whenever we can have electron delocalization, we will have a more stable molecule, more stable system. So that concept is that we need to be using when we are solving problems. And also in regards to what is the heat of hydrogenation. So typically, the more stable the molecule is, upon hydrogenation, let's say that I do a reaction, I need to do this reaction, and I do a hydrogenation, And when I do that, of course, I'll be adding hydrogens across the double bond. There is a release of energy. The reaction is exothermic, and this is negative 239 kJ per mole. When the molecule is conjugated, this amount is smaller, meaning that it's lower in energy. If we had, and I'm gonna now erase this to draw another molecule. Say that we think that of the heat of hydrogenation this time of a molecule that will have 4 carbon but only 1 double bond. So trying to investigate where there is less stable or more stable the conjugated system, I'm gonna say that I'm gonna use 2 of those, of course, to have 2 moles similar to that, and I do the hydrogenation reaction. And what I found is that the heat that is released here is larger upon the hydrogenation. So this is negative 254. Again, joules per mole. This is, think about something potential energy here is higher than this. Upon hydrogenation, this energy potential, and it's like when you do potential energy depending on the height, and then it will go into kinetic energy. So this will have less conversion into heat than this. And so the more delocalized, the more stable it is, the less heat. So you will find questions about asking which molecules will have less heat of hydrogenation, which will evolve less heat. So now you can relate that to structure. The more delocalized, the less, say, exothermic will be, less heat of hydrogenation.